On this video, we'll do some review problems to prepare for the test on Chapter 3.6 to 3.10. First, let's talk a little bit about the natural log of x versus the natural log of the absolute value of x and their derivatives. So, the natural log of x, if you recall, has a restricted domain. So it's only defined for x greater than 0. And we say that its derivative is 1 over x, but that's actually not entirely true, or we should say that we don't somehow magically gain domain. So 1 over x is defined for everything except for 0. But if we start with the natural log of x, we don't really get a domain that includes the negatives. So we're still only getting that part, even though we don't have to say that. That's supposed to be understood. So sometimes what's done is to extend the domain of a natural logarithm so that it will match the domain of its derivative, 1 over x, is to put it in absolute values. So in the blue here, you can see what the graph of the natural log of absolute value of x looks like. You kind of have to use your imagination. They're supposed to be mirror images of each other. It doesn't really look like that. Now, it's still not defined at x equals 0. There's an asymptote there. So the natural log of absolute value of x is not defined at 0. But by putting it in the absolute values, it becomes defined for both positives and negatives. The question then becomes, what's its derivative, or how do we get its derivative? So let's talk about that a little bit and kind of maybe allay your concerns here. So for the absolute value of x, we know its definition is defined as a piecewise function. When you put in a positive number into an absolute value, the absolute value just leaves it alone. It's just that same face value. The absolute value of 5 is 5. The absolute value of 9 is 9, and so on. Now, when you get a negative number, the absolute value changes it to a positive. The way it does that is to multiply it by negative 1. So the absolute value of negative 2 is the negative of negative 2, that is, is positive 2. So when we look at the derivative of the natural log of the absolute value of x, we have to look at it as a piecewise function, because it is. So when x is positive, greater than or equal to 0, well, and it's not going to be defined at 0, so let's not even worry about the equal to 0 part. But when it's a positive number, then the natural log of the absolute value of x is just the natural log of x, because the absolute value isn't doing anything. Therefore, its derivative is going to be 1 over x. Now, when you have a negative number, then the natural log of the absolute value of x is really the natural log of the negative of x, right? You're plugging in a negative number for x, so the absolute value multiplies it by negative 1 to make that positive so that it might be defined in the logarithm. So now when you take its derivative, it's a chain rule derivative. You're going to take 1 over the u, that's the negative x, times the derivative of negative x, which is negative 1. You can see those negatives cancel, and you get, excuse me, 1 over x. So the takeaway, what I want you to take away from all of this is that you really don't have to worry about that whole absolute value thing. So the derivative of the absolute value, the natural log of the absolute value of x, is just 1 over x. Now the domains of these two match. As you can see in the blue curve here, the natural log, and the 1 over x, the original green, is going to be its derivative. Okay, let's go on and talk about logarithmic differentiation. This is a technique that we use when we have a function raised to a function power. It doesn't follow any of the other logarithm rules or any other differentiation rules. So what we're going to do in the case of, say, y equals x to the x is we're going to take the natural log of both sides. That will allow us to use our property of logarithms to bring that exponent out in front. Then we're going to do implicit differentiation. So the derivative of natural log of y is 1 over y times y prime, or y prime over y. And the derivative of x natural log x is going to be a product rule. So that's going to be the first x times the derivative of natural log x, which is 1 over x, plus the second natural log x times the derivative of the first, which is just 1. We're going to multiply this y to the other side, so we'll get y times. Now the x times 1 over x is just 1, plus natural log x, and then we'll go back from calling that y to what we said it was originally. So it's x to the x times 1 plus natural log x. And there is our derivative using logarithmic differentiation. Okay, let's try another one. You might want to pause the video and try it on your own. I'm going to jump on in. So we're going to take the natural log of both sides. And so when we do that on the right side, we can bring that sine x out in front. So we can now do implicit differentiation and get y prime over y is equal to the product rule now, sine x the first times our 1 over x plus the second natural log of x times the derivative of the sine x, which is cosine x. We can multiply the y to the other side, and I'm just going to call this sine x over x. And I don't really have a great way of writing this one, so I'm just going to say natural log x times cosine x, so it doesn't look like either the cosine is in the logarithm or the logarithm is in the cosine. And then we'll go back to y, calling y the x to the sine x that it was originally, and I'm just going to leave that as sine x over x plus the natural log of x times the cosine of x. And there we have it. There is our derivative using logarithmic differentiation. Now, let's do some derivatives of logarithms and refresh our memory. We need to, since this is a logarithm base 10, we're going to first convert that using our change of base before we try to take the derivative. So that's going to be the log of the base that we want, the natural log, over the natural log of the old base. Now to find its derivative, we're going to just think of this as a constant 1 over natural log 10 times our logarithm of x squared plus 1. So it's going to be that constant 1 over natural log 10 that's just hanging out times the derivative of the natural log of u, which is going to be 1 over u times du. And that's pretty much the end of the story. If you want, I guess we could just make that a natural log 10 times our x squared plus 1. And that's our derivative. Now the second one, before we get carried away in trying to find g prime with this very complicated inside of the logarithm, let's do all of the algebra that we can using our properties of logarithms. So we know a logarithm of a division is the difference in the logarithms. So I'm going to write that as x squared plus 1 to the 1/2 minus the natural log of 3x minus 5 to the 4th. We can use more properties of logarithms and bring those exponents out in front to make them just constant multiplication. And so we have the 1/2 times the natural log of x squared plus 1 minus 4 times the natural log of 3x minus 5. Now we're finally ready to actually do some calculus and take those derivatives. The constant 1/2 is going to hang out. Again, we get our 1 over u times du. Similarly, the 4 is going to hang out, and we'll get our 1 over u times du. We'll do a little bit of cleanup here. We can cancel this 2 with that 2, and so that'll become just, that'll become x over x squared plus 1, and that's going to be a minus 12 over 3x minus 5, and that is painless as we can make that derivative. Okay, I'm going to slide the screen up, and let's see if we can take the derivative of the natural log of cosine of x. So remember, the absolute value is just going to disappear once we take the derivative. We don't have to worry about it any longer. It should not appear in the derivative. So we're going to get 1 over u, which is cosine of x, times du, the derivative of cosine, is a negative sine x. And then we can recognize that as our familiar tangent of x. So our derivative is going to be a negative tangent of x. Now, the next one is a chain rule. So we have the 1 minus 16x squared is sitting inside the square root, which is sitting inside the arc sine. So our derivative, our formula here, is going to be for an arc sine is du over the square root of 1 minus u squared. So this whole thing is the u. So the du itself is going to be a chain rule derivative, because our u is that 1 minus 16x squared to the 1/2 power. So this is going to be kind of complicated. So I'm going to go du, that's going to be 1/2 times 1 minus 16x squared to the negative 1/2. Now we've differentiated that square root part. Now we're to the inside, the 1 minus 16x squared, its derivative is a negative 32x. So all of that is the du. Now we're going to have the square root of, and we're going to get our 1 minus u squared. So that's 1 minus the square root of 1 minus 16x squared squared. Okay, let's clean up a little bit to the numerator. The 1/2 and the 32 are going to cancel. So that's going to leave us 16. So I'm going to write that as a, and we'll still have that negative sign, so that's a negative 16x. Now I'm going to move this negative 1/2 exponent into the denominator. So that's going to become a square root of 1 minus 16x squared. Now I'm going to direct my attention to what's happening in here. Now when we square that radical, that's going to remove the radical. So that's going to become 1 minus now the quantity, 1 minus 16x squared. So that negative sign here is going to have to distribute. So that's going to be 1 minus 1 plus 16x squared. So we can see the ones will kill each other off. Once they're out of the picture, then we're free to take the square root of 16x squared. Now be careful. The square root of 16 is indeed 4. The square root of x squared is not x. The square root of x squared is actually the absolute value of x, because this has to be non-negative. So that is going to be an absolute value of x there. Well, let's see what we can and cannot cancel. We can cancel the 4 with the 16. So that's going to become a negative 4, and that, but this x and that absolute value of x cannot cancel because they are not always the same for all values of x. So we're going to still have that absolute value of x, and we're going to have this square root of 1 minus 16x squared in the radical. Whew, that's complicated. All right, let's scroll up here and see if we can now first find an equation of a tangent line to that function at x equals 0. So to find a tangent line, we need a point. And to get a point, we've got the x-coordinate is 0. We need to know its y-coordinate. So that means we're going to get 4 plus the sine of 0 to the 3/2. Sine of 0 is 0, so that means we have 4 to the 3/2. So that's going to be the square root of 4, which is 2 cubed, which is 8. So that gives us our point is 0, 8. And notice that's also a y-intercept. Now to get an equation of a line, we also need the slope, and the slope is going to come from the derivative. So let's find that derivative using our chain rule. So we have this 4 plus sine x raised to the 3/2. So we're going to go 3/2 times 4 plus sine x, leaving this inside function alone, to the subtract 1 from the exponent. Now times the derivative of the inside function, and the derivative of 4 is 0, the derivative of sine is cosine, and so this is our derivative. We want to evaluate that at x equals 0. So that's going to be 3/2 times 4 plus the sine of 0 to the 1/2 times the cosine of 0. Well, sine of 0 is 0. 4 plus 0 is 0. Square root of 4 is 2. That 2 is going to cancel with that 3/2, and the cosine of 0 is 1. That's going to make our slope be 3. So we take our point and our slope. Well, we actually have the y-intercept. So we can write our tangent line. This is now our answer to part A, is y equals 3x plus 8. Now part B, we're going to use the tangent line to approximate f of negative 0.2. So that means we're going to put in negative 0.2 for the x. And so that's going to be 3 times negative 2 is negative 0.6, and that's going to be 7.4. So this is our approximation to f of negative 0.2 using our tangent line. Okay, let's see what we can do to use this idea, this tangent line approximation idea, which is what a linearization is. It's just using a tangent line. Whoops. So let me get back to what I want. Didn't want the highlighter there. So we want our linearization. So we're going to try to come up with a function to approximate the square root of 79. So that function is going to be the square root function. We want to pick a value for x that's close to 79, but that works out very nice. And so I think the perfect square that's closest to 79 is going to be 81. So we're going to find the tangent line to the square root of x at x equals 81. So again, to get a tangent line, we need a point. So we want f of 81 is the square root of 81, which is 9. So our point is going to be 81 comma 9. We need the slope, and that's going to come from the derivative. So taking the derivative of x to the 1/2 is going to be 1/2 x to the negative 1/2, which is 1 over 2 square root of x. So our slope is going to be that derivative evaluated at our x value, which is going to be 1 over 2 times the square root of 81, which is 1 over 2 times 9, which is going to be 1/18. So now we have our slope and our point. So together we get a tangent line that's y minus 9 equals 1/18 times x minus 81. Now we want to use this tangent line to approximate the square root of 79. That means we're going to use, in our tangent line, we're going to plug in x equals 79 and find out what that y value is. So we're going to get y equals, I'm going to add the 9 to the other side, we're going to get 1/18 times x, or 79 rather, minus the 81, because we're going to plug in the 79 for x. That's going to be 9 plus 1/18 times a negative 2. So if we believe in canceling, that is going to become 9. Whoops, I didn't really want to go white there. I'm going to go back to green. So we have 9, and then it's going to be a minus 1/9. So if you can imagine borrowing 1 from that 9, that would be 9/9, minus the 1/9 is going to be 8 and 8/9. And that's our approximation. Okay, let's scroll on down here and see if we can do a little implicit differentiation here. So let's see, we're going to take the derivative here. So the derivative of natural log of u is 1 over u times du. The du is the derivative of x plus y, which is going to be 1 plus y prime. We're going to have to come back there and split that apart so that the y prime will go different side of the equal sign than the 1. The derivative of secant y is secant y tangent y times y prime. And now we're going to do our product rule. So different people do it different ways. I'm going to pull out that negative, and now we're going to go the first 3x squared times the derivative of y cubed, which is going to be 3y to the second times y prime, plus the second y to the third times the derivative of the 3x squared, which is going to be a 6x. And then the derivative of 2 is 0. So now I'm going to do a little cleanup before I move things around. This is going to be 1 over x plus y plus a y prime over x plus y is equal to, I'm going to bring the y prime in front for secant y tangent y, and then distribute that negative sign. The numbers migrate to the front, so that's going to be a minus 9 x squared y prime, and then a minus 6xy cubed. Now we're ready to start moving stuff around. I'm going to leave the y primes on the left side. So there's the y prime over x plus y. I'm going to come back and put the equal sign somewhere over here. I'm going to move this 1 over x plus y to the other side by subtracting it. I'm going to move the y prime secant y tangent line to the left side by subtracting it. I may not have left enough room here. And then we still have this minus 6xy cubed on that side, but I'm going to try to add this to the other side and squeeze it in here as a plus 9x squared y prime. Okay, let's move up to, get my pen back, let's move up here. I'm going to factor the y prime out of this stuff on the left side. That's going to leave us with a 1 over x plus y minus the secant y tangent y, and then that plus 9x squared y squared that I'm trying to shoehorn in there. Then our equals, close that off. That's equal to, on the other side, our negative 1 over x plus y minus 6xy cubed. And then finally, we're going to divide all that stuff to the other side. So our y prime is going to be negative 1 over x plus y minus 6xy to the third all over 1 over x plus y minus secant y tangent y plus 9x squared y squared. We're not going to try to do any simplification. I'll be very happy if you can get to this point right here. All right. Let's see on this next one if we can determine if the mean value theorem applies to f of x equals 1 over x plus x on the closed interval from 1 to 3. If it does apply, can we find the points guaranteed by the mean value theorem? So this is trying to force us to understand what the conditions are for the mean value theorem. So the conditions for the mean value theorem is that f is continuous on the closed interval, continuous on our closed interval from 1 to 3, and it must be differentiable on the open interval 1 to 3, which it is. And the reason for that is the only place where this has an issue with continuity and differentiability is going to be where it's undefined, which is at 0. So I'm just going to say in parentheses, f is continuous and differentiable for all x not equal to 0. So we have met the criteria there. So then what the mean value theorem claims is that f prime of c must equal f of b minus f of a over b minus a for some c in this interval from 1 to 3. So now we're going to set about trying to show that. So we're going to need the derivative. So let's see, f prime of x. This 1 over x is x to the negative 1. So its derivative is going to be negative x to the negative 2. And the derivative of x is 1. I'm going to maybe write that in a little more friendly form as 1 minus 1 over x squared. We'll come back to that. We need to know what is f of 3. F of 3 is going to be 1/3 plus 3. I'm going to call that 3 is 9/3 plus 1/3 is 10/3. F of 1 is going to be 1 plus 1 is 2. I'm going to think of that as being 6/3. So f of 3 minus f of 1 over 3 minus 1 is going to be 10/3 minus 6/3 all over 2. That's going to be 4/3 over 2, which is 4/3 times a half. We can cancel, and that is going to be 2/3. That's our f of b minus f of a over b minus a. So we can now, I'm going to switch colors here. So I'm going to take our f prime, 1 minus 1 over x squared, set that equal to 2/3, and try to solve this for x. And hopefully we're going to find something between 1 and 3. If not, this will be a momentous occasion because this theorem has stood for hundreds of years, and we will have found a counterexample that will make me rich and famous. I kind of hope it doesn't work. If we subtract 1, that's going to be a negative 1/3. We can multiply through by the negative 1. We can cross multiply or take the reciprocal of both sides to get x squared equal to 3. We want all possible solutions, so that's going to be plus or minus the square root of 3. Now our interval, remember, was from 1 to 3, so square root of 3 is bigger than 1 and less than 3. Negative square root of 3 doesn't fit, so our only value is going to be c is the positive square root of 3. Crazy. Let's go on. We're going to use Newton's method here to approximate the zeros of f of x equals x cubed plus x plus 1 to 5 decimal places. So if we graph that on our calculator, it looks like it is going to cross somewhere in the neighborhood. I think it's between -1 and -2. I'm just going to choose a first guess of -1. It doesn't matter what you use, we just have to communicate that. We're going to need to know the derivative, so let's make sure we do that. The derivative is going to be 3x squared plus 1. Now, you need to make sure that you communicate to me that you know what the form is for our Newton's method. And that's going to be x sub n plus 1 is x sub n minus f of x sub n over f prime of x sub n. So then we're going to do this on our calculator, but we're going to have to show what we get as we move along here. So I'm going to, on my calculator, I've already got the function entered in as y1, so I'm going to go y equals, and I'm going to put the derivative 3x squared plus 1 in as y2. And so then I'm going to go second mode, quit and go to the home screen. So I'm going to take -1, store that as x and hit enter. Then I'm going to go x minus, then variables, right arrow, enter, enter, and go parentheses x. So now I'm taking x minus f of x, then divide that by back to variables, right arrow, enter, down 1 to y2, enter parentheses x, close the parentheses, store that as a new x. Now when I hit enter, I'm going to get that the second guess, or the first approximation after my guess of -1 is going to be a -0.75. Then I'm going to just document what we get here. I'm going to hit enter again, and now we're going to get -0.68604665, I believe is what I've got. Now I'm looking until we can get agreement to 5 decimal places, and then I need to know the 6th place so I can round it accurately to the 5th place. So let's see. Now I'm going to hit enter again, and now I'm seeing -0.68233958. So now we have agreement to 2 decimal places. I need more than that, so I'm going to hit enter again. So now here is my x of 5, and now we've got -0.682328. So now we have agreement, it looks like, to 1, 2, 3, 4 decimal places. I think I'm going to have to go again here. Here's enter, and this is now x sub 6. And we're seeing -0.6823278, 23278, and it goes on, but I think this is going to be enough. We have agreement to 1, 2, 3, 4, 5, and then we can see that the 6th place is 5 or bigger, so I'm going to say that that is going to be approximately -0.6823, and then that's going to round to 3. So there we have it, to 5 decimal places. All right. Now, the next question is trying to see if you can do this without using your calculator, just to kind of get the concept behind it. So we want to use Newton's method just to get a general rule for approximating the 4th root of c. So Newton's method approximates zeros of functions. So we need to think of a function that has as its zero the 4th root of c. And so that would be, our f of x would be x to the 4th minus c, right? Because if we set that equal to 0 and solved it, we would get the 4th root of c. So since the 4th root of z makes this function equal to 0, Newton's method will find the 4th root of c when we find the 0. So now what we're going to do is, as we did before, communicating. The derivative is going to be 4x to the 3rd. We know that x to the n plus 1 is going to be x to the n minus f of x sub n over f prime of x sub n. So we are going to get, let's see, f of x sub n is going to be x sub n to the 4th minus c over, I'm sorry, I left off the x sub n. Let me back up. Let me erase this. So I need the x sub n first. So that's going to be x sub n minus. Now when we plug in x sub n into our function, we're going to get x sub n to the 4th minus c over, when we plug in x sub n into our derivative, that's going to be 4x sub n cubed, and I'm okay with that. You could go on and get a common denominator and make that more formulaic, but I'm okay just with this. Okay, let me see if I've got more. Oh, I do. Okay, so we have now the volume of a cube is v equals s cubed, where s is the side length of that cube. The side length is measured to be 6 inches, but maybe we've got an error in measuring of up to 0.04 inches. Use differentials to A, approximate the maximum possible error in calculating the volume. So if we can't measure the side length perfectly, then when we compute our volume, that error in measuring is going to get magnified, and we want to know by how much. So we know that that our volume is s cubed. We know that the error in measuring that side length, our delta s, we're going to call that our differential ds is the 0.04. Our actual side length is 6. We're trying to estimate the error in our computation of the volume using our differential dv. So we start with our v equals s cubed. We'll take the derivative of the volume with respect to s, and that's going to be 3s squared. We'll multiply the differential ds to the other side, and so we get dv is equal to 3s squared ds. We can now plug in the numbers we know, so it's 3 times 6 squared times the ds we're going to call 0.04. So 6 squared is 36. 36 times 3 is 108. 108 times the 0.04, if I use my calculator, is 4.32. So that is our approximation to the error in computing the volume. And so let's give units with that. So that's going to be 4.32. Since it's a volume measure, that's going to be in cubic inches. Now the relative error, we're going to take our dV and divide that by the actual volume so we can see relatively how much are we off. So that's going to be our 4.32 over the volume, which is going to be our 6 cubed. So 6 cubed is 216. If we take the 4.32 divided by the 216, we're going to get 0.02. So that is our relative error. And then to make that percent error, we'll just move that decimal over and call it 2%. So an error in measuring the side length of 6 inches, if we're off by 0.04 inches, that's going to result in a 2% error in computing the volume of that cube. All right.